Hello guys, in this video we'll start to learn how analog signals can be used in industries. After a short introduction, I'll configure my analog input module in the Semantic Manager software, and I'll start a simple project to show you how I can use my analog input and output modules. During the project, you'll learn how NFC block can be used to define a function, and also some floating point and converter instructions will be explained and used. Let's start the video. Until now, we have done some projects with digital inputs and outputs. At the beginning of this tutorial, I explained my PLC hardware and also its wiring. We know digital sensors or push buttons have two states, on or off, open or closed. These devices can use 0 and 24-volt DC to send their status to the digital inputs of my PLC. Also, the digital outputs of my PLC use 0 or 24-volt DC to turn off or on a digital actuator such as this signal lamp. On the other side, much industrial equipment such as level transmitters or flowmeters and also some actuators work with analog signals. For example, a voltage between 0 and 10 or between -10 and 10 volts. A current signal between 0 and 20 milliamperes or between 4 and 20 milliamperes. Naturally, we need more than one bit to store and use these signals. Usually 16 bits are used for analog signals. Let's see an example. Well, here is a level transmitter to measure the level of a substance such as wheat or salt. This transmitter can be tuned to generate a voltage between 0 and 10 volts when the level of substance is between 0 and 50 meters. My PLC can receive this signal using its analog input module and then converts it to an integer number between 0 and 27,648. Notice we need to use the user manual of each PLC brand to find these numbers. See this user manual of Siemens about the S7300 modules. Let's select the fourth chapter, Principle of Analog Value Processing. Well, here is useful information about the analog signals, their wiring, and so on. Now pay attention to this table, which shows how my S7300 PLC converts a bipolar signal, such as a voltage between -10 and 10 volts, to an integer number. The important part of each signal is its rated range. So, based on this table, when the received signal is in its rated range, the PLC converts it to an integer number between -27,648 and 27,648. The next table is related to unipolar signals, like a voltage between 0 and 10 volts. In this case, when the signal is in its rated range, we'll have an integer number between 0 and 27,648. Well, the next table is specifically about the bipolar voltage. For example, if I select this signal type for my analog input module and this voltage appears at the input, I'll have this number, 1, in my program. Similarly, you can use the next tables related to the other analog signals. Now, let's select the next section, representation of analog values for analog output channels. We can use these tables to generate a specific electrical signal at the analog outputs of an S7300 PLC station. For example, if I select this range for my analog output module, I should use this number in my program to generate this voltage at an output of my analog output module. Well, another important point is related to the analog input modules, which are supplied with corresponding measuring range modules as required. You may have to change the position of these square modules to select the correct measurement type and range. Note that the optional settings of these measuring range modules are A, B, C, and D, and a short description about each option is printed on the analog module. Well, in Chapter 6, we can find useful information about each analog module. For example, I'm using an analog input module with this article number. As you see, here is useful information like the wiring diagrams. I'll use the first channel of my analog input module, I mean channel 0, to receive a voltage between 0 and 10 volts. And also I'll use channel 2 with this wiring diagram to receive a current signal between 0 and 20 milliamperes. Okay, now let's see how we can receive an analog input signal and convert it to the process value in the Semantic Manager software. If you remember, I configured my PLC station in the previous videos. Well, as you can see, I have one analog output module with 4 channels and one analog input module which gives me 8 input channels. As you know, I can double click on each module and then change its settings as required. First, let me change the default addresses of the analog input module. Note that I've used input bytes 0 to 3 for my digital input modules. In consequence, I cannot use them right now. The next free address is 4. Now, parts 4 to 19 are reserved for my analog input module. Again, let's double click on the analog input module and then select the Inputs tab. Here I can change some settings. First, I need to select the correct signal type for each input channel. Let's select the voltage option for the first 2 channels, I mean channels 0 and 1, and select the current signal with 2 wires for channel 2 and 3. Because I want to use the next channels, I've selected the first option for them to deactivate these channels. Note that I also need to select this measurement type on the analog module. Let me show you how you can change the position of the measurement type and range modules. Well, as I mentioned earlier, I can select options A to B with these square modules. Note that here you can see a short description about each option. Now let's change the position of the last square module. Note that the position of the first 2 modules are B and D, as well as my settings in the Semantic Manager software. Okay, let's continue. I wired my analog input module based on this wiring diagram. Now I only need to connect its first and last pin to a 24-volt DC power supply. Alright, until now I've selected the voltage item with this rated range for the first two channels, and also the current signal with two wires and this range 4 to 20 milliamperes for channels 2 and 3. Another point is that I connected channel 0 and channel 3 of my analog input module to the outputs of this device. It's a signal generator that can generate a voltage between 0 and 10 volts and a current signal between 0 and 20 milliamperes. Now let me show you what will happen if I choose a wrong settings. As you know, I selected option B on the analog module for the first two channels. Let's change it to A and then transfer the hardware settings to my PLC. Okay, before transferring the hardware settings, I need to power my PLC station. Again, let me try to transfer the hardware settings to my PLC. As you can see, my PLC has turned on the system fault LED on the analog input module because its settings are not matched with the selected settings in the Semantic Manager software. Now let's solve this error by selecting the correct measurement type. Okay, as you see, the system fault LED on the analog input module has been turned off. Until now, I configured my analog input module in the Semantic Manager software. And as I mentioned earlier, I've connected its channel 0 and 2 to the outputs of this signal generator. Now, before starting the programming step, I should answer this question. What are the addresses of channels 0 and 2? As you see, bytes 4 to 19 are used for the analog input module. Note that each channel needs 2 bytes of the input image memory. In other words, 1 word or 16 bits. So these are the addresses of the 8 channels of my analog input module. Okay, let me save the current hardware settings. Then I'll write a program to use these two addresses to read the generated voltage and current signals by this device. Well, I connected the outputs of this signal generator, which are a voltage signal between 0 and 10 volts and a current signal between 0 and 20 milliamperes to these two addresses of my analog input module. I want to write a program to read these two signals. Like the previous videos, I can start the programming step from the main organization block, OB1. Notice I'll need to use my codes twice to read the two signals. So a better way is to create a function or FC block with this name, read analog signals. Inside the FC1 block, I'll use this mathematical function to read an analog input signal and convert it to its related process value. Note that I can call FC blocks as many times as I need by the main organization block OB1. Okay, usually each function has some inputs, outputs, and maybe some internal variables. I need three inputs. Naturally, the first one is the received analog input signal. Remember, it's an integer number between 0 and 27,648 when the received signal is unipolar within its rated range. Also, I need to determine the height and low scales of the input signal. According to the hardware settings, if I want to read the voltage generated by my signal generator, these two inputs will be 10 and 0. Note that I've selected the real format for these two inputs because I'll write my program codes in real format because of this division in the mathematical function. The real format uses 32 bits to store real numbers. You can use the help window to see more details about this format. Well, my function has one output, the process value, which can be the received electrical signal or an industrial parameter such as level, temperature, flow, and so on. Okay, I also need some internal variables to implement the mathematical function. First, let's define two variables. I'll use them to change the format of the received analog input from an integer number to its real format. As I mentioned earlier, when I receive a unipolar signal within its rated range, my analog input module gives me an integer number between 0 and 27,648. First, I want to change it to a real number. So let's select the converter instructions. Note that there isn't any instruction to convert an integer number to a real number directly. First, I have to change the format of integer numbers to double integer format. After that, I can use this instruction to convert them to real numbers. Now let's use floating point instructions to implement the mathematical function. First, let's use a subtraction instruction to calculate this part of my mathematical function. Well, I need another internal variable to store the result of the subtraction. Note that the output of this instruction is a number in real format. Now let's define more internal variables and then use the floating point instructions to implement the mathematical function. Okay, based on this user manual, if my analog module receives a unipolar signal within its rated range, the signal will be converted to an integer number between 0 and 27,648. So I need to enter this number here. Note that the inputs of this instruction should be real numbers. So I need to add the fractional part of 27,648 too, which equals to 0. Well, let me compile the program based on the mathematical function. Finally, I need to restore the result of the mathematical function as the output of the FC block. Let me save the program and exit from the FC block. Now let's open the main organization block, OB1, to call the FC1 block. Okay, as you see on the left side under the FC blocks folder, I can find my FC block. Let's add it to the first network and determine its inputs and output. Remember that I connected the voltage output of my signal generator to the first channel of the analog input module with this address, which its range is 0 to 10 volts. And finally, I need a double word memory to restore the result of my function, because it's a real number. Similarly, let's use the FC1 block to read the current signal, which was connected to channel 2 of the analog input module. Now let's save the program and transfer the project to my PLC. Alright, I've downloaded the project successfully. Now let's open the OB1 block. Note that my signal generator has a mini switch to select its voltage output or its current signal. First, let's select the voltage output. As you can see, the first FC1 block calculates the voltage signal correctly. Okay, now let's select the current signal. As you can see, the second FC1 block calculates the current signal correctly. Okay, for this example, if I want to calculate the level of substance, and instead of reading the voltage signal, I'll need to change these two inputs in my program to 0 and 50 meters. Well, as you can see, if I change the voltage signal, the output of the first FC block will change between 0 and 50 meters. Alright, until now, I've explained how to read analog input signals. Now let's see how I can use my analog output module. It generates an electrical signal based on the number which receives from the CPU. Usually it should be a number between 0 and 27,648 for unipolar signals. First, let's check the hardware settings of my analog output module. Okay, this is my analog output module. First, let's change its default addresses. Note that my analog output module can generate both voltage and current signals. I only connected its first channel to this analog voltmeter. So let's select the voltage item and then an appropriate range, 0 to 10 volts. Now let's save the hardware settings. Now let me test my analog output module with a simple program. Remember, I selected 0 to 10 volts as the rated range for the first channel of my analog output module. So I need to use the move instruction to send 0 and 27,648 numbers to the first channel of my analog output module with this address to generate voltage 0 and 10 volts. Also, I can generate 5 volts at the first output of my analog output module by sending this number. Note that this table from the Siemens user manual shows more examples. Now let's set the program and transfer the project to my PLC. As you can see, my PLC station can generate 3 different voltages at the first output of my analog output module. Alright, I hope you learned how to use analog signals in industries. Now we are going to design a water tank system in Factory I/O to learn how to use analog equipment such as valve, level meter, and so on. And I'll use scale and unscale functions to display the current and desired level on two digital displays. At the first step, let's launch Factory I/O to design a water tank system with its control box. Well, let me add a water tank station. Note that the tank supports two modes, digital and analog. In this video, we are going to learn how analog signals can be shared between the Factory I/O software and the PLC scene simulator. As you can see, there are two analog instruments at the top of the inserted tank. The fill valve can be controlled with a voltage between 0 and 10 volts, and the level meter generates a voltage between 0 and 10 volts when the level of liquid changes between 0 and 300 centimeters. At the bottom, the discharge valve can be controlled with a voltage between 0 and 10 volts, and also the flow meter generates a voltage between 0 and 10 volts based on the flow of water. Now let's design a control box for the inserted tank. Okay, now let's select appropriate names for the inserted push buttons, potentiometers, and digital displays. Well, by default, the inserted potentiometers generate a voltage between 0 and 10 volts. I'll select the second mode, minus 10 to 10 volts, for the second potentiometer. As you see, by default, the digital display can be used to show a real number between 0 and 10 volts. Let's select the integer mode for the two inserted digital displays. I'll use them to display the current and the desired level of the liquid inside the tank. Alright, I've designed my control box. Now let's open the File menu and select the drivers item to modify the connection settings. I'll use the S7 PLC Sim Simulator as my controller. Now let's click on the configuration item to change the number of inputs and outputs and also check out other settings. Now let's connect the inserted equipment to these inputs and outputs with these addresses. Alright, I finished the connection settings between Factory I/O and the PLC Sim Simulator. Now let's launch the Semantic Manager software. Well, let's create a new project. Now let's launch the PLC Sim Simulator. Well, let me select the MPI port for the virtual PLC and connect it to the equipment in Factory I/O. As you can see, Factory I/O has connected to the virtual PLC successfully. Note that I'm going to use the PLC Sim Simulator to test my program codes. So it's not necessary to configure my Semantic 300 station, and I can select the S7 program item. The next step is programming. Before that, let me open the symbols table and define suitable tags for my PLC inputs and outputs. Alright, these are my PLC inputs and outputs, and I can use them with these tags during the programming step. Now let's open the main organization block OB1 to start this step. Well, I want to open the field valve with the first start push button. Note that the field valve is an analog valve and I cannot use a call to turn it on. I should use the move instruction to send a number to open the field valve. Well, I should send this number 27,648 to generate 10 volts at the output. Similarly, let's use the first start push button to send 0 to close the field valve. Now let me save and test the program. Well, this message says a call or assign is required. So let's use a call with a bit of memory to solve this problem. Notice the set of this address is not important to me. Now let's download and test the program. Well, based on my program, I can use these two push buttons to open and close the field valve. As you can see, when I press the start push button, this number 27,648 is moved to the output address QW30, and the analog module generates 10 volts, which can open the field valve completely. Now I want to open the field valve 50%. So let me send this number to QW30 address and then test the program again. Okay, similarly, I can use this logic for the discharge valve, but I wanna use the first potentiometer to control the discharge valve. Remember, the potentiometer generates a voltage between 0 and 10 volts. Also, the discharge valve is controlled by a voltage between 0 and 10 volts. So I only need to use a simple move instruction. The virtual PLC receives this voltage at its input and converts it to an integer number between 0 and 27,648. Then the move instruction moves that to this output directory. Then the PLC will generate a voltage between 0 and 10 volts, which can open and close the discharge valve. Now let's write a program to receive the analog signal from the level meter to calculate and display the current level. Remember that I wrote a function for this purpose with the floating point instructions. Now I want to show you an easier method to read analog signals. As you can see below the basic instructions, there are some predefined functions. Let me find the scale and unscale functions under the standard library. Well, let me open the help window to see more details about the scale function. Here we can see the mathematical formula, the data type of the inputs and outputs of the scale function, and so on. Note that the scale function receives an integer number and gives us a real number. Now let's use that to receive the level meter signal and convert it to a real number between 0 and 300 centimeters. I need to connect the first input to the level meter, IW30. As you can see, the level meter tag has not appeared here. Why? To solve this problem, I need to open the symbols table and change its data type. Note that the first input of the scale function, FC105, receives an integer number. Well, as you see, Semantic Manager has added the scale function FC105 to my project. Now let me open the symbols table. I need to change the data type of the level meter input from word to integer format. Similarly, let's change the data type of the two analog inputs which are connected to the two potentiometers. As you can see, now I can connect the level meter tag to the IN input of the scale function without any error. Okay, let's continue. The low and high limits of the water inside the tank are 0 and 300 centimeters. It should be entered in real format. Finally, the last input is used to select the signal type. It's either bipolar or unipolar. The level meter signal is unipolar, so I need to connect the last input to a false logic. As you know, the result of this part of my program is always false. On the other side, a word address of memory is used for the first output. The second output gives us the water level in real format. Well, here is an error. I need to change the data type of this memory address from double integer to real format. Now I want to show this number on the first digital display. Remember, the selected format for this address is real, and it's not suitable for the two digital displays which receive integer numbers. Here, let me show you a simple technique using the unscale function. This function receives a real number and gives us an integer number. Based on this formula, if I select the unipolar signal mode and also these numbers as its high and low limits, Then the unscale function converts the data type of its input without changing its scale. You can hit this page of the help window to learn more details about the unscale function. Now let me use the unscale function to convert the data type of this memory address. Well, the output of the unscale function is an integer number. I need to select this data type for the outputs, which are connected to the two digital displays. Alright, the third network receives the level meter signal, converts that to a real number between 0 and 300 centimeters, and then converts that to an integer number, which can be read by the first digital display. Similarly, let's write a program to select the desired level using the second potentiometer and shows its value on the second digital display. Note that the second potentiometer generates a bipolar voltage between -10 and 10 volts. So the last input of the second scale function should be connected to a true logic. Well, I finished the programming step. Now let's download that to the virtual PLC, which is connected to the designed water tank system in the factory I/O software. Okay, as you can see, the first network can open the field valve 50% and close it completely. Let's modify the program to open the field valve completely. Well, based on the second network, I can use the first potentiometer to control the discharge valve. Okay, as you can see, the third network, this is the level meter signal and converts that to a real number between 0 and 300 centimeters. Then this number is converted to an integer number, and you can see that on the first digital display. Finally, based on the last network, I can use the second potentiometer to select my desired level and display it on the second digital display. Okay, with this program, I can control the level of water manually. I mean, an operator is needed to open and close the valves and check the level of water continually. For example, now the desired level is 254, and I need to use the control box to change the level of water. Now the current and desired level are close together. In the next videos, I'll explain and use some methods to control the level of water automatically. Thanks so much for watching this video. Take care.